Okay, so in this case, we are asked to give all the possible rational zeros. And before I do that, I encourage you to look up something called either the rational roots theorem, this is important, or the other one, the other variation is the rational zeros theorem. Okay, so this it goes by either one of these names, it's the same thing. But what it says, in essence, is that if you have a polynomial and it has integer coefficients, so these are integers, of course, all right, and then every rational zero of p, so not irrational, but only rationals. So if, say, for example, pi was one of the zeros, that would be irrational. This theorem wouldn't work for that case. So every rational zero of the polynomial is of the form p divided by q. So what is p? Well, p is just a factor of this constant right here. And q is a factor of the leading coefficient. Okay? So a lot of times students have trouble remembering, well, which one of these is p, which one of these is q. I draw this really weird little picture, and I'm not much of an artist, but I draw my P, I draw my Q, and then I draw what I say is a little dog. Some people might say, oh, it looks like a rabbit. I don't know. But here's the head, here's the tail, and let's think about it this way. Here's the head, here's the tail. So in this case, Q is 2, and P is this -8. All right, so we're going to do something with that shortly, but let's go ahead right now and list all of the factors of P and all of the factors of Q. So what numbers multiply to give me 8 or -8? What factors multiply to give me 2? So this, remember, is plus and minus 1, 2, 4, and of course 8 itself, so always plus and minus. And the factors of 2, since it's prime, are 1 and 2. So now what we're going to do is we're going to take all the p's and divide them all by q's. So the first case here is that we're going to take all of these p's and divide them by 1. So let me put all possible, and I just usually put all possible rationals, all right, implying that I mean zeros, all right? All possible rationals. So we're going to take all of these and divide them by 1, but that's going to give us those numbers exactly. So I'm going to rewrite them, plus and minus 1, 2, 4, and 8. And then we're going to take all of them and then now divide them by the second q, in this case, which is 2. So 1/2, 2/2, 4/2, and 8/2. The last step here is to get rid of all of the duplicates. So all of the duplicates in this case, well, none of these are duplicates. This isn't a duplicate. But what's 2 divided by 2? That's 1. 4 divided by 2 is 2. And 8 divided by 2 is 4. And we already had those. Okay? So all the possible rationals are these guys right here. So these are all the possible rational zeros. Okay? So what we would do to find out if these were the zeros, and at most this polynomial will have 3 zeros because it's a third degree polynomial. But what we would do is probably do 1, 2, 3, 4, 5. So there's 5 times 2. We probably want to do 10 synthetic divisions here with each of these cases. So 1, -1, and see which one gives you a 0. Because if it's 0 by the factor theorem, when you do that, you should have a remainder 0. So this is what we're doing here. So let's take a look at this next example. All right. So again, we identify the P and the Q. Remember, the P is the tail and the Q is the head. So the P in this case is 18 and the Q in this case is the -2. All right, there we go. And so what do we have here? Well, we got 1, we've got 2, we've got 3, we've got 6, we've got 9, and of course we can't forget 18. And again, -2 here, the factors again being 1 and 2 because it is prime. Okay, so all possible rational zeros, all possible. Again, I just put all possible rationals. Okay, so what does that look like? That's all of these guys divided by 1. So 1, 2, 3, 6, 9, and 18. And then you're going to take all of them again and divide them all by 2. Let's go ahead and do that. 1 over 2, 2 over 2, 3 over 2. We've got 6 over 2, 9 over 2, and 18 over 2. So now what we're going to do is, again, is eliminate any of the duplicates. None of these are duplicates. This is not a duplicate, but here we get 2 out of 2. 2 out of 2 is the same as 1. We get rid of that. 3 out of 2 is not a duplicate. We keep it. 6 out of 2 is the same as 3. We get rid of that. 9 out of 2 we don't have. And then we have 18 out of 2, which is 9. So we're going to get rid of that, and then we're going to keep these right here. All right, so these right here comprise our possible rational zeros. And again, to find the actual zeros, of course, in this case, there might be up to 4. We would do, 1, 2, 3, 4, 5, 6, 7, 8, 9 times 2, so about 18 synthetic divisions. Or you could plug these into your calculator and see which ones give you zeros, because those would be the zeros. All the possible rational zeros is all this set, but the actual zeros, you get 0 when you plug it in and evaluate the function at any of those numbers. So again, a possibility of 4 in this case. But this is a little bit about the rational roots theorem, and good luck.